Well, hello. We are going to continue on with some exponent stuff. So what we're going to do today is we're going to look a little bit more carefully at rational exponents. We touched on it yesterday, or last lesson, I guess. We're going to continue on with that, and then do some actual practice questions with some numbers and some other stuff just to get us up to speed. Make sure that we're down with the exponent rules and laws. Okay, so this is, more exponents. Hope everyone had a nice, long weekend. Hopefully we're going to have some, campfires and stuff like that now that the fire ban's off. All right, on we go. So just as a review, I would like you to express as a single simplified power for the following. Express as a single simplified power the following. So how about if we had 3xy cubed squared to the times 3 squared x cubed y z squared to the fifth all over 3 cubed x to the negative 4 y z cubed. Okay, so express that as a single simplified power. And I guess single is really a misnomer. Express it as the most simplified power that you can. Okay, so single, there's going to be more than one, but I would like you to write it as the most simplified power you can. Go ahead, work on that, and I'm going to solve it now. Okay, so the first thing that's worth recalling, I've mentioned this, but I'll mention it again, is that any power that doesn't have an exponent showing, that doesn't mean that the exponent is 0. It really means the exponent is 1. So I would always advocate to you that anything that doesn't have an exponent on it, you go along and you put an exponent of 1 on there so that you don't forget that there is an exponent in play. It's just 1. We don't write it because if it's not written, we know that it's 1. Okay, so then we're going to simplify the powers first. So when we have a power, or in this case, a few powers, to an exponent, we simplify by multiplying the exponents. So the first step is going to be, this is going to be 3 squared x squared y to the sixth. Okay, and then we're going to do the same thing over here. And also it's worth noting that after I expand a power to an exponent, we get rid of those brackets. Okay, so same thing here. I'm going to get rid of these brackets. So we're going to have 3 squared to the fifth. That means it's going to be 3 to the exponent 10. And this is going to be x to the exponent 15 and z to the exponent 10. Okay, and then the denominator, it doesn't really get to play this time around, so it's just going to be here for now. So I'm just going to rewrite it. Y to the first, z cubed. Now, next, I think I mentioned this in a prior video, but if I didn't, I'm going to remind you. There are implicit brackets. Implicit means we know they're there, it's not explicit. So there are really brackets that go around the entire numerator and the entire denominator anytime that you have a rational expression like that, okay? So what that means is I'm going to have to fully simplify this numerator before I can do the division. Okay, so that's what I'm going to do. So we're going to have multiplying powers with the same base. So there's a base of 3, there's a base of 3. We're multiplying. So we multiply powers with the same base. The base remains unchanged, still 3. And we add the exponents. 10 plus 2 is 12. And then x squared times x to the 15th is x to the 17th. And y to the 6th times, there are no other y's. So it's just going to be y to the 6th. And then we have, there are no other z's. So there's just z to the 10th. Let me go back up and make sure that I copied that down properly. I missed one. Hopefully you spotted that. There is a y to the first to the fifth. So really in here, there should be a y. 1 times 5 is 5, which is going to come back here and change this because now we have y to the 6th times y to the 5th, which is, of course, y to the 11th. So let's grab our eraser here, and we will fix that. Embarrassing. Okay, to the 11th. And there we go. Lovely. So, and then the denominator, it still is just kind of hanging out. It hasn't come into play yet. So here we go. X to the negative 4, y to the 1, z cubed. Now, we know that when we divide powers with the same base, the base remains unchanged, and we subtract the exponents. So there's my base that matches. I subtract the exponents. 12 minus 3 is 9. Oh, and this is where it gets tricky. We're going to subtract the exponents. 17 minus, now it's not minus 4, it's minus negative 4. When I subtract a negative, it's like adding. So this is x to the 21. And then 11 minus 1 is y to the 10th. And 10 minus 3 is z to the 7th. Okay, so that's what it is when we express as a simplified power. Now I said single power, and really there's 1, 2, 3, 4 powers. So single power was not really appropriate. But what I mean if I say that again, and generally what someone would mean is that you would write it as the most simplified power possible. So there we go. Lovely. So that's review. All good. Just for the sake of saving some paper, as it were, I'm going to kind of block this off and work over here. So we talked a bit about an exponent of 1/2. So if I said, hey, what is 100 to the exponent 1/2? We said that, oh, when we have the exponent of 1/2, it really means square root, right? So you could type that into your calculator as a square root. You could type in the root of 100, right? So you could say, oh, I realize that this is functionally the same thing as the root of 100, and you could go ahead and type it in there like that. Alternatively, depending on your calculator, you could type in 100. On my calculator, it's usually the button that looks like that up arrow. It's called a caret to the exponent, and I could say 0.5 because that's the same thing as a half, and it would give me 10, which would, this one also give me 10 as well, clearly. Some of you would have 100, and then you've got your button that is, x to the y, or alternatively y to the x, and to the 0.5. And 0.5 works because a half is nice. Or if you have brackets, you could do 100 to the exponent 1 divided by 2 and put those in brackets, and you're still going to get 10. So that's all well and good as long as the exponent that's a fraction is 1/2. You can just say, oh, it's a square root. But I'm going to introduce you to what happens when we have a rational exponent that is something other than 1/2. Rational just being a fancy name for exponent, or for a fraction, excuse me. So imagine that instead what we had was we had an exponent of, let's say, 2/3. So imagine that we had the number 27 to the exponent 2/3. Now I couldn't type it in as 0.5. 0.5 is a nice exact fraction. This as a fraction, or as a decimal, excuse me, is 0.6 repeated infinitely. So if I were going to type this into my calculator, and really I'm going to teach you how to do this when you wouldn't even need a calculator to do this, but you would type it in as hopefully 27, and then you would hit whatever your exponent button is to the exponent, and then in brackets you do your 2 divided by 3. If you type that in, I'm hoping when you type it in, you get 9, and you might think, what on earth? So I want to look at the general form of a rational exponent. We're going to debrief on what that means, and then we'll come and revisit this. So we will be back for that. So I'm going to leave myself some space to come and, solve here. But we're going to look now at what it means to be a rational exponent. So rational exponents, or fraction, I'll put that in brackets, fraction exponents. So rational exponents of the form, we're going to kind of get a little technical here. So of the form, a to the m over n. So this is just the general form. Can be rewritten as, this is going to get a little bit sketchy, but it's all right. We're going to write it as the nth root, and the n comes from there, of a to the exponent m, or we could rewrite it, and it's almost the exact same thing. It is still the nth root of a but that whole thing is to the exponent m, okay? And this is confusing, it's weird. And so I'm going to teach you a rule that my math teacher in high school, her name was Mrs. Kirkham, and she was amazing. And you didn't slight Mrs. Kirkham for fear of your life. She was a little bit strict. But here is the rule she taught me way back when to how to remember what the heck is going on with a rational exponents. So I'm going to introduce you to something called, I'm going to grab a dark color here, the caret rule of rational exponents. Now, this will not be found in any mathematical textbooks, I promise you. This is I don't know if it's her creation or not, but I've shown it to a bunch of my friends when I was at Waterloo, and I've taught some other teachers about this, and they all think it's goofy, but it's one of those things that's because it's goofy, we remember it. So the caret rule of rational exponents, and we'll talk about how this is. So I'm going to break out my mad art skills. I hope that's black or brown. And then I'm going to get, what's down in here? That I'm looking for orange. I think that maybe is orange. I have no idea. Looks orange to me. So what we have is, you can probably guess, this is going to be a caret. And now I need green. Is this, I have no, that looks green to me. Let's pretend that's green. So there are the leaves on the caret. And now I need some yellow. Is that yellow? I think it's maybe yellow. And we have the big ball of joy up here. No, it's not, Cam. It is the sun. Okay, so there's the sun. And you're like, what? Okay, so here is why this is called the caret rule of rational exponents. So I'm going to rewrite that rational exponent. So a to the exponent m over n. Okay, so where do carets get their power from? Well, the carets get the power from the sun. So carets get power from the top. So the top of the rational exponent is the power. And the bottom of the caret is, of course, the root. And so the bottom of the exponent is the root. So it is called the caret rule of rational exponents. It's stupid, but it's easy to remember. When we have a rational or fractional exponent, the number on the top is the power number. The number on the bottom is the root number. Okay, power on the top, root on the bottom. So if we go back up here, this is how we're going to do this. This one we know is the power number. This one we know is the root number. So it doesn't matter the order that we do it in. We can do it in either one, like I've shown down here. This one has the power happening before the root. This one has the root happening before the power. And it is good in either case. If you want to do, if you're going to just do it in a calculator, then you're good to go right there. Like, boom, you can just type it in. You don't even really need to know that this is the power and this is the root. But if I rewrite this, this is the third root, right there, third root of 27. And then that is going to be raised to the power, or to the second power, the exponent of 2. So I know that three numbers that multiply, and this is third root is probably not a great example here, but nevertheless, three numbers that multiply that are the same to make 27 are 3 times 3 times 3. So the third root of 27 is 3. So that piece evaluates to 3, and the squared is still around. 3 squared, well, 3 squared is 9. And there it is. That's why I said 9. Okay, so it's a silly rule, but it's one of those rules that, because it's silly, you remember it. So the caret rule of rational exponents. We've got the power on top, we have the root on the bottom. So what I'd like you to do is, I'm going to write a couple of expressions, and I would like you to write them in the other form. So this is written in like the powered root form, and this is written with the rational exponent. And we're going to go back and forth on a couple of examples just to see that we've got this. So we're not going to evaluate them, we're just going to rewrite them. So imagine that we had 7 to the 4 fifths. What would that be in the powered root form? Okay, so go ahead, pause it, write it down. Here I go. I'm going to say that this is the root on the bottom, so it is the fifth root of 7 to the exponent 4. That's one way we could write it, or we could write it the fifth root of 7 to the exponent 4. Either one of those is acceptable. Okay, let's try one more just like that. How about if we had 18 to the exponent 7 quarters, right? Go ahead, write it in the powered root form. Okay, here we go. Well, this is going to be the fourth root on the bottom, of 18 to the exponent 7, because the power is on top, or the fourth root of 18 to the exponent 7. There we go. I'm going to write one now in the powered root form, and I want you to write it in the rational form. Okay, so imagine that we had the sixth root of 8 cubed. And you're like, that's a weird one. This is actually an interesting one. Okay, so the sixth root of 8 cubed. So 8's the base, still the base. We know the power goes on top, so the power goes on top, and the root goes on the bottom, So 8 to the 3/6, which is exactly what it is, and I would accept that, but that's a fraction that I can reduce, and fractions can be reduced. So you could rewrite that as 8 to the 1/2. So it's interesting, the sixth root of 8 cubed is actually the same thing as, well, that's just the square root of 8. Okay, let's try another one. How about the 11th root of 5 to the 10th? Okay, so there it is in the powered root form. Go ahead and write it in its rational form. Okay, so the base is still the base, it's 5. And we've got the power, it goes on top. And the root, it goes on the bottom. And there it is. And that one, you couldn't write it any other way. Now, evaluating this, again, if you're going to evaluate this on your calculator, you would type in, 5, and then you'd hit whatever your exponent button is to the exponent, and then you would type, hopefully you have brackets, 10 divided by 11. Now, you're like, well, I don't have brackets, Galbraith, and it's like, that's going to be a little bit more challenging. If you didn't have brackets, what you would need to do is as follows. You would need to type in, so this is only for the kids who don't have brackets on their calculator, and their calculator is, a direct entry thing. So you would have to do 10 divided by 11 and hit equals, and it would give you a number. It's going to be a decimal, like 0.9 something, like 919 or something like that. So you'd get that decimal, 0.9-ish, whatever it is. And then you'd have to, it would be in your interest to write those decimal places down, and then you would say 5, and then you'd hit your exponent button, so your x to the y, I think all of those calculators are, and then you would type in whatever that number was, and you would get the answer. Much easier if you have a 2-line calculator that has brackets, and you type it in like that. Okay, so there we go. So that's like the last rule that we really need to examine. We're going to do some practice combining some of these things now. So let's kind of amp it up a little bit. So imagine that I said, what is 3/4 to the exponent negative? That's too big. How about negative? Let's go easy. Negative 2. And I would like this expressed as a simplified fraction. Okay, I don't want this as a decimal. Now, certainly, if you had a calculator, you could type 3 divided by 4 in brackets to the exponent negative 2, and it would give you some not very nice number. It would be something akin to, I don't know, like 1.7 repeated, I think is what it is, something like that. But what we're going to do here is we're going to use our knowledge of exponent rules, and we're going to simplify this and write it in a simplified form. So first things first, notice we've got this negative, okay? We're going to have to address that first. The negative I think we talked about, I'm hoping we talked about, it's going to take and it's going to reciprocate, flip the base, right? So we're going to flip the base on this. So the first thing that we're going to do is we're going to say, well, the base of this power, right? Because this whole thing is a power. This whole thing is a power. And we're going to reciprocate this as the base. So we're going to flip that over. So it's going to become 4/3. And then that's all that negative did, is it's caused the base to reciprocate. So this is going to become 4/3 squared. We got rid of that negative. So the negative caused the base to reciprocate. Okay, good so far. Now, I know that there's really an exponent of 1 on this guy and really an exponent of 1 on this guy, because every power, and that was true over here as well, I just wasn't going to use them, right? I know that when I have a power, or in this case, a couple of powers, to an exponent, I simplify by multiplying the exponents. So this is going to become 4 squared over 3 squared, okay? So, if I was just going to leave it as a power, that'd be good. But we can do this. We know that 4 squared, 4 times 4, well, it's 16. And 3 times 3 is 9. So there is that expression simplified as much as we can do, right? So there we go. That's lovely. So yeah, there we go. Nice, nice, nice. Let's try another one. How about if we had, let's do 25/16 to the -1/2. Combining a lot of stuff here. So go ahead, take a stab at this if you want. Not if you want. I'd like you to take a stab at this. Welcome back. I'm going to give it a whirl now. So here's what we're going to do. We're going to say, all right, this negative is going to cause the base to reciprocate, right? We're going to flip this base. So it's going to become 16/25. And all that that's done is it's handled the negative. So this is still to the exponent 1/2. Okay, lovely. And then we're going to say, all right, well, that's good. So these really have an exponent of 1 on them. They did up there too, but I wasn't going to use it, so I didn't write them in. When I have a power to an exponent, I simplify by multiplying. So 1 times 1/2. Well, 1 times anything is just anything. So this is going to be 16 to the 1/2 and 25 to the 1/2. Lovely. Now, I remember that 1/2 is the same thing as square root. So 16 square rooted is, well, that's 4. And 25 square rooted, well, that's 5. And there it is, written as a simplified fraction. Okay, which, if you typed it in your calculator would just have dumped out 0.8, which is a nice enough number. But it's nice to know where it came from. It came because we reciprocated the base, and then we, used the power to an exponent rule, and we multiplied the exponents. And then we knew that a rational exponent, the root's on the bottom, the power's on the top. Really, this is just square root. Square root of 16 is 4. Square root of 25, 5. Lovely. Okay, let's do another one. How about if we had 8 to the exponent -4/3? Oh, that's a doozy. We're going to try and do this without a calculator as well. Now, we're going to handle a negative first. The negative causes us to reciprocate the base. And you're like, oh, well, maybe I just write the 8 the other way around. And you're like, haha, there it is. No, okay, not that. We know that every number can be written as a fraction by putting it over 1. So I put it over 1. And that means that, I'm going to have to get my eraser out. That means that when we, did I not select it? Must not have. No, I did. Stop that. Why are you, there we go. When we go to flip this guy, what we're going to have is it's going to be 1/8 to the 4/3, right? So 1/8 to the 4/3. We got rid of the negative. The negative caused the reciprocal to happen. Lovely. Now, I know there's really a 1 on this guy, and there's a 1 on this guy. So when I have a power to an exponent, I multiply the exponent. So this is 1 to the exponent 4/3 divided by 8 to the exponent 4/3. Now, anything, 1 to the exponent anything is 1, because you square root 1, you multiply 1 by itself a zillion times. 1 to the anything is just 1. So we're good there. 1. Now, I can look at this and see what it is. Most of you couldn't. So I'm going to take this is in the rational exponent form, and I'm going to convert it to the powered root form. So here we go. I know the base is 8, right? The root is from the bottom, because just that's where the root on the caret is, on the bottom. So the root is the third root. And we have to the exponent 4, because the power comes on the top to the 4. Now, we could have put the 4 in there as well. The reason I did this is because I can take the third root of 8 in my head. I can't do 8 to the exponent 4 in my head. Could I? I might be able to, but I wouldn't be able to do the third root of it in my head. So the third root of 8. What three numbers that are the same multiply to be 8? Well, I've chosen this on purpose. It is 2, right? The third root of 8 is 2. You could type that in your calculator, third root of 8, and you would get 2. Now, I haven't really addressed how we would type this into our calculator. Some of you, if you look around, you will find an actual button that looks just like that with nothing in there, or potentially with an X in there. And that's how you would get the third root. That only is good if it's third. If it was fourth or fifth, it's like, that's not going to work. So most of you, or pretty much all of you, will have a button. It's probably going to be on your second function row. It's going to have this with a little X in it. And so to access that button, if I wanted to do the fifth root of something, I would do 5, this button, the xth root of something, and then you would type in whatever you wanted to do. So like 15, and that would find you the fifth root of 15. So if I wanted to find the third root of 8, one way I could do it is I could find the button like that on my calculator, or I could do 3 powered root button of 8 equals, and then it would say, oh yeah, that's 2. Yeah, okay. Now back to where we were. The third root of 8 is 2. I've still got to the exponent 4. I know that 2 times 2 times 2 times 2 is 16. So the answer to this is 1/16. Okay. So those are some practical examples. And you're like, this is really, it's kind of out there. This doesn't come up a ton in even the math that I would do, although it's a building block for the next piece that we're going to get to. As I've suggested, this doesn't seem financial mathish yet, but we're getting there. This is all building the capacity and the depth of understanding for when we actually hit some of the financial math formulas that you are going to be responsible for. Okay, so I will find some homework questions and post those on Google Classroom. Lovely. Thanks, guys.